today we get to do the same thing that we did with the sine and cosine, but now we're going to work with the secant and the cosecant and the cotangent and the tangent. So we're going to do some of the same darn things. So first of all, you don't have to write this down, but we want to walk through this together to make sure that we're keeping track of our reference angles, remembering those. This is good. We have to keep repeating. Those flashcards that you can use can also be a good way to keep reminding yourself, hey, what's the sine of pi over 6? What's the cosine of 3 pi over 4? So let's build our table. Sine of 0 is 0 because it starts in the middle, right? What's the sine of pi over 6? 30-degree angle, it's going to be 1/2. The sine of 30 is 1/2. A 45-degree angle, pi over 4, square root of 2 over 2. Pi over 3, square root of 3 over 2. What happens at 90 or pi over 2? 1. That's where it gets to be as high as it's ever going to be. Okay? And then what happens at 2 pi over 3? 2 pi over 3 is suddenly a 60-degree angle in the second quadrant, right? So it's square root of 3 over 2, and sine's positive there, so we'll have a positive square root of 3 over 2. What happens at 3 pi over 4? Square root of 2 over 2. Still positive. We're in the second quadrant. How about the 5 pi over 6? 1/2. Still positive. We're in the second quadrant. What happens at pi? 0. We get to be a 0 again. That's the middle point where we're in the middle of our graph again. Okay? Now, what happens down here at 7 pi over 6? Negative 1/2 because the tangent's positive, the sine is negative. How about 5 pi over 4? Negative square root of 2 over 2. Anytime we see a 4 in the denominator for a sine, we know it's a square root of 2 over 2. We just have to figure out what sign. How about down here at 4 pi over 3? Negative square root of 3 over 2. All right, 3 pi over 2, we're down here at 270. Negative 1, that's the lowest point that the sine wave gets to be. 5 pi over 3. It's a 60-degree angle in the fourth quadrant. Negative square root of 3 over 2 because cosine and the secant are going to be positive in that quadrant. How about a 7 pi over 4? Negative square root of 2 over 2, it's a 45. In the fourth quadrant, sine's negative, and 11 pi over 6. Negative 1/2. All right, let's do the same for cosine. Cosine of 0 degrees. What happens at 0 degrees for cosine? 1, it starts high. How about at pi over 6? Square root of 3 over 2. Pi over 4. And pi over 3. 1/2. And what happens at pi over 2? 0. That's when we get one of our zeros of the cosine. We hit the middle. And then what happens at 2 pi over 3? It's second quadrant. Cosine's negative, so negative 1/2. And at 3 pi over 4? Negative square root of 2 over 2. 5 pi over 6? And what happens at 0, or at pi? Negative 1. And then at 7 pi over 6? 30-degree angle, so it's a square root of 3 over 2. Tangent's positive, so cosine is negative. And at 5 pi over 4? Right? And then what happens at 3 pi over 2? 0. 5 pi over 3? 1/2. Positive now because cosine's positive. 45-degree angle in the fourth quadrant for cosine? Positive square root of 2 over 2. And a 30-degree angle for cosine? Square root of 3 over 2. Finally, tangent. Okay, what happens to tangent when we're at 0 degrees? Because we take sine divided by cosine and we get 0, right? But what happens at the 30-degree angle? All those 3's, we get square root of 3 over 3. The tangent of a 45, 1, because we divide, we get 1. And the tangent of a 60, plain old square root of 3. Doesn't have as many 3's. What happens when we try to divide sine over cosine to get tangent at pi over 2? Undefined. And what happens at 2 pi over 3? Another radical 3 because it's a 60-degree angle over here. Okay, and it's positive still. Okay, and then what happens at negative? Because we're in the second quadrant. We're right here. So that's going to be negative. All right, thank you. Next one, 3 pi over 4. And at 5 pi over 6, square root of 3 over 3 is a 30-degree angle. It's in the second quadrant where sine's positive, so it's negative. Okay, now we're down here at pi. What happens to tangent at pi? It gets to be a 0. 0 divided by negative 1 is 0. We're okay, we're not breaking any laws. What happens at 5 pi over 4? Sorry, 7 pi over 6? Square root of 3 over 3 is a 30-degree angle, so it's got all those 3's, and the tangent is positive in this third quadrant, so it's positive. And then what happens at the 45? Positive 1. What happens at the 60-degree angle? Square root of 3. Doesn't have all those 3's. It's a 60. What happens at 3 pi over 2? Undefined. And then what happens at 5 pi over 3? 60-degree angle, so a square root of 3, positive or negative? Negative. It's in the fourth quadrant. Tangent's negative. How about at 7 pi over 4? Negative 1. And finally at 11 pi over 6? Gotta remember them. Can't lose track of those. Okay? The reason that we really wanted to look at this is because we're going to talk about the tangent, and we want to talk about where we get these lovely asymptotes. Okay? We're going to have asymptotes at pi over 2 and at 3 pi over 2, and zeros at the 0 and the pi. Okay? So here we go. So this is the graph of the tangent function, and we talked about it a while back. What was the period of the tangent function? Pi. So this is the one that breaks the rules. Everybody else, sine, cosine, and cosecant, secant, were always 2 pi. But tangent and cotangent like to do their own thing, and they have a period of pi. So we have to remember that when we're doing a phase shift, or not so much a phase shift, but our period, our part B. Okay? So we said the domain was everyone except for these asymptotes, right? So x could not be pi over 2 plus, how frequently do these occur? Every pi. So pi n. Pi k, k pi, whatever you want to call it. Where n is some constant integer. Okay? And the range we said was negative infinity to positive infinity. Okay? And so the vertical asymptotes are pretty much exactly what we have in the domain, right? X equals pi over 2 plus pi n. Okay? Now, why does that happen? Well, let's think about what's happening at, well, this is pi over 2, right? So what happens so this is 90 degrees. If your calculator's in degree mode, what happens to the tangent at 89 degrees? What is the tangent of 89? Grab a calculator, put it in degree mode real fast. Mode, degree, tangent, 89, 57.28. Okay? So that's why it's shooting clear up to the sky. And what is the square root of 3 for 60 degrees? Square root of 3 is 1.7. So here is our pi over 2. This would be pi over 4. 15 degrees away would be 1.7. So we're almost up here at 2. Okay, let's not even go that extreme. Let's just figure out what the tangent of 70 degrees is. And we're at 2.74. Okay? The tangent of 80 is 5.67. Okay, so when we're clear up here at 5.67, we're at 80 degrees already. And then it just shoots off to infinity. Does that make sense to everybody? Okay, so next then, we want to talk about how the A, B, C, and D are going to impact our tangent. Okay, so first of all, if we have y equals 2 times the tangent of 2x, what's happening here? Changing our asymptotes, and we're going to change, what's this guy? We have two 2's. What's the first 2? A for would typically be amplitude, right? We talked about how it doesn't have an amplitude, right? So since the tangent doesn't have an amplitude, what's that still going to do to it? Stretch it, right? It's going to pull it up higher. So everything's going to shoot up faster than it would have normally. Okay? So when we look at this guy, see how they're a nice, easy curve, right? But think about what's going to happen with that. If this was the point 0, 1, pi over 4, 1, it's now going to be pi over 4, 2, isn't it? We're going to double that value. So it's going to shoot up higher faster. It's not going to have as wide of an arc. And if it was a fraction, it's going to flatten it out and not let it take off as quickly. That makes sense, everybody? Okay? All right. What's the other 2 going to do? That's going to be the period. So that's going to change how frequently we get a new tangent curve, or whatever you want to call it, a new iteration of it. So if b is 2, what does that mean? Twice as many in a period. What is the normal period for tangent? Pi, so now it's only going to take half of pi to finish it, right? So we're going to get a complete tangent wave, or tangent curve, in pi over 2, and we'll get 2 of them in its normal pi. Okay. Now, where were our asymptotes before? Every pi over 2, pi over 2 plus pi n, right? So will we have one at pi over 2 now? No, because we got to get 2 things going on in that time, right? Where's our asymptote going to be? Pi over 4. It's going to adjust it, isn't it? We're going to have an asymptote at pi over 4, and we'll have a 0 at pi over 2 now, and at 3 pi over 4, we're going to have another asymptote, and then another 0 at pi. So it's changing that parent function because of that b. So here are our new asymptotes. Okay. If I put 0 in for x, do I still get 0? The tangent of 0 was 0, right? So we have a 0 here. We have a 0 at pi over 2. And what happened with this guy? Well, at what was pi over 4, it was 1, right? Now it's going to be pi over 8 is going to be 1 up. And this 2 is actually going to change it, so it's not 1 up, it's 2 up, isn't it? It's going to stretch that guy vertically. So pi over 8, we're going to be all the way up here at 2 already. So it's going to make it a very steep looking curve. Okay, stretching it way out. So we're taking what would normally be the value at, when we like pi over 4, because the tangent of pi over 4 is traditionally 1, right? But we had to switch it because we have changed this now. So it's going to be at pi over 8, we're going to get what would normally be our 1. But this number, this a, which isn't really an amplitude in tangents, but this a is going to stretch it. So instead of being up at 1 at pi over 8, I would be up at 2. It would be higher. So we're going to, the 0, unless we change the phase shift, will still be a 0. Does that make sense? Just when we shift it left or right, that we'll have to adjust that. You wouldn't normally. We would never know the value of pi over 8 because it's not one of our special angles. So what I'm looking for, I'm not looking for perfection on tangent, okay? What I'm looking for is that you have your asymptotes in the right places, that you have your zeros in the right places, and that if it's stretched, that you try to make it look like it's stretched. And if it's shrunk, that you try to make it look more flattened. Does that make sense? I'm just looking for an honest effort here because we're not going to take the time to plot individual points. Does that make sense? But I want to give you a reference for why this guy's heading up so fast as it is. Does that make sense? Okay. Just like we're not plotting all the little 30s and 45s and 60s on our sine waves either, right? We want to get the nuance of what the graph is doing. No. But we do know that the easy one is always a pi over 4, right? And so a pi over 4 is going to be a 1. That's a good frame of reference. But now that we have changed the period of it, it's not going to be a pi over 4 that we would have a 1 now. It'll be half as big because we're having to shift it over. Everything's shrunk. And so now we're going to get a 2, so it's just going to shoot up faster and shoot down quicker. Okay, same thing here. It's going to shoot up faster and shoot down faster. So between 0 and pi over 2, we have now gotten one full complete graph. We have our top and we have our bottom. So we have one full cycle, one full period. Make sense to everybody? I think I have another tangent example. I have a cotangent example, okay? Absolutely. And I think I have a cosecant and a secant and then a cosecant with lots of stuff going on. Okay? Trying to elongate it, make it look steeper. All right, so far so good? Other questions on this one? Okay, next one. So let's play with cotangent now. Okay, so we said that tangent was undefined at pi over 2 and 3 pi over 2. So where is cotangent undefined? Pi and 2 pi and 0. Okay, so those are going to be our asymptotes now. And just like a tangent had a period of pi, cotangent will have a period of pi. Okay, so we need, if we're trying to get two full cycles of our graph, then we want to make sure that we have 0 to 2 pi or negative pi to pi. Okay. Pi is where we stop. That's where we can stop because we can get one full cycle to show it. And then we can stop at negative pi as well. So with cotangent, now we have asymptotes where? Zeros and pi's, every zero, every multiple of pi. Okay. Here. Okay. Now, let's think about what's happening. At pi over 2, what was cosine? Oh, sorry, what was tangent? Cotangent. If it's not undefined at pi over 2, it's going to be 0. And at negative pi over 2, it's also going to be a 0, right? Now, toward, this is pi over 2, toward the right-hand side, what was it doing on tangent? Going up, right? Because those numbers were getting bigger. But if we flip them and put them in the denominator, what's happening to them? Yeah, they're going to go up the other way. These are going to go up and these are going to go down. Does that make sense? Okay. So we have something that looks like this. We get this nice little S curve going on either side. Because think about what's happening at, so this is at pi over 2, right? Okay, so our tangent at pi over 2 was undefined. Okay, and so what was happening was at through this. So this is pi over 2. We had an asymptote here. Okay? And what happened at pi over 4, halfway between? We're up here at 1, right? So that guy's going up like this, and we had a 0 over here. But what's happening now at pi over 4? It still gets to be this 1, right? That part hasn't changed. But when we were at pi over 3, we were at the square root of 3 over 3, okay? Which is smaller than square root of 3, isn't it? So when we flip it, now we're at square root of 3, so now it's going to be higher. At pi over 3, it's going to be higher, and the square root of 3 over 3 is going to be lower. So think about your 30 and your 60 being in between here. Okay, the 30 degree is now going to be the square root of 3, so it's going to be higher. The 60 degree is going to be the square root of 3 over 3, so it's going to be lower. Okay, the positives and negatives don't change. We're still in the same quadrants and so forth, but instead of being heading up, we're now heading down. Okay, so far so good? Other questions about this one? Okay, so now let's play with the cosecant, remind ourselves what that one looked like, and then we'll actually move them. So the cosecant is the reciprocal of sine. So what I recommend is that you do a ghost image of a sine in dashed lines or something, very light pencil marks, so you can see what's happening, and then you know how everything else is going to work. So on a sine, we have a normal period is 2 pi. And its normal amplitude is 1. And so on a sine, we typically start where? High, middle, low, and the 0 in the middle. Okay? So sine, we start in the middle, we end in the middle, and in the middle we're in the middle, right? And which way do we go first? Pi. So at pi over 2, we're at 1, and at 3 pi over 2, we're at negative 1. So we're just going to dash this in, so we have that pattern to work our way through. Okay. Now that's the kind of it helps us get a framework, because we know that cosecant is going to be outside of this box, outside of this frame. It doesn't get to be any of that except for those 1s and negative 1s. Now what happens when we had a 0 for the sine? What's the cosecant going to be? Undefined. We get an asymptote there. And at pi over 2, the sine is pi over 2. Well, if we reflect it or find the reciprocal, we're still going to get a 1. So we'll have a point here, and it will head to the sky toward this asymptotes. We'll have a point negative 1 at 3 pi over 2, and it'll head towards its asymptotes. Point at negative 3 pi over 2, and a negative 1 at negative pi over 2. So you see how knowing the sign helps you build the framework for the cosecant? Okay, so now let's play with that. Let's do a secant this time, but let's change this to a secant plus pi over 2. So secant's the reciprocal of cosine. That means that we need to sketch a cosine graph. What's happening with the pi? Left pi. So we've got the reciprocal of cosine. Okay. Say to the negative 1, that's an inverse. Okay, and we're going left pi. So our normal period for cosine is 2 pi. But we need to shift it back to the left pi. So this is the start of our frame, and we're going to finish up at pi for one complete cycle. Amplitude hasn't changed. And so our zeros and so forth are going to now be our asymptotes. So where does cosine typically start? At 1, so it's going to start high at that negative pi, end high, and in the middle it's going to be low, and then the other 2 points are going to be middles. So this is where our cosine would have been if we shifted it left pi, and now we have to figure out where our asymptotes are going to be. It doesn't hurt to do another little cosine wave here. So let's put our asymptotes in. Anywhere we see zeros, we make asymptotes. Yep, because remember we shifted our cosine left pi, so that's going to shift our secant left pi as well. Make sense? Okay, so if you shift that parent function to the left, that's going to help you with the reciprocal function. Okay, so now we should have something that looks like this. Sense? Questions you have? All right. So we have one last one, and then we'll talk about assignment, whether we want to do a worksheet or a book assignment. Worksheet? And then we'll talk tomorrow about whether we need more practice with that book assignment. Okay, does that make sense? So I think the worksheet I had is going to be a really good one because it will really help you emphasize what A, B, C, and D all do, and then it has some graphing on the back. So, okay, so we're going to graph this guy. So y equals negative cosecant of x plus pi over 4. So we've got 1, 2, 3 things going on here, don't we? What's the negative going to do? Reflect it. Okay, what's the 3 going to do? Stretch it. Yep, it would be the amplitude if we were talking about the sine, right? But it's going to stretch it. Exactly. So instead of having a nice wide parabola, we're going to have something that goes faster. Does that make sense? It's going to make it's going to shoot up faster. Okay? And if it had been a flattener, we would have something that has a very elongated view. Okay? If it had been like a fourth or something like that, a fraction. Okay? All right, same thing with tangent. Just going to make it go do its thing faster. All right, so negative 3 cosecant x plus pi over 4. What is the plus pi over 4 doing? I'm always, for some reason, I'm going left on these. Should have done some rights. Okay. So let's sketch out our ghost sine image. Okay, because the reciprocal of cosecant is sine, right? So, yep, absolutely. We're going to do exactly everything that way. All we have to do is just make our shape things. Okay? So, what would happen with sine? Shifted to the left. So we got to start out by shifting to the left. So we would normally have our 4, but we're shifting left pi over 4. So we're going to shift to here. So these are our new new guys. Okay, so this would be our new starting place, right? It would be our new 0, but what's happening? The negative 3 is going to do what? Going to make it go down to as low as 3, isn't it? Okay, so we're going to go down to negative 3, up as high as 3, right? And sine starts in the middle, right? And then it ends in the middle, and in the middle is in the middle, right? So if this was our sine, starting in the middle, ending in the middle it's in the middle, but now we're having to stretch it down here, aren't we? And we're going to stretch it up here because of that reflection and because of the 3. Does that make sense, everyone? Okay. So if our sine wave was here, where do we put the asymptotes? The zeros. Okay. So we've got asymptotes now here, here, pi over 4, 3 pi over 4, 5 pi over 4, negative pi over 4, right? I did put that in the wrong spot. 2 of them in the wrong spot, wasn't it? This one. It's that one. Not too crazy. My dashes. Okay. And so now what's happening? For now, practicing 1 period. When we get to the test, we want to do 2. Okay? Good. It's good. Good to practice, do it the whole way. I just don't know how much time you have or how perplexing these are, how much you're having to think through. 2 periods on the test. So yeah, you probably should practice it that way, but I want to give you time to work, so I'm trying not to spend that time repeating. Make sense? All right. So assignment, I can give you a worksheet instead. We may come back and do one more day. I have time at the end of the semester to play with, and so if we feel that we need more time, one more day on graphing this stuff by tomorrow, we can spend one more day on graphing these, or we can use it for something else. Does that make sense?